Okay everyone, welcome to 1.3 continued, the intermediate value theorem. Alright, I'm doing this video years after, well a couple years after I made the other chapter 1 videos. So you'll notice the intro page looked different. I'm sorry about that. You'll notice I have this ugly watermark down here. I'm sorry. Long story, I'm not going to get into it right now. Let's just get right to the video. So it's a bit of a random topic that I didn't realize was in the curriculum. So I'm adding it in here, but it's not the biggest deal in the world. It's just kind of a bit out of left field. But we usually talk about this when we're talking about continuity, which we've been doing, I guess, last video. The intermediate value theorem states that if f is continuous, so if a function is continuous, remember, the basic way you can think of continuous is a function you can draw without lifting your pencil. If it's continuous on the interval from a to b, including a to b, and if w is any number between f of a and f of b, then there is at least one number, c, in that interval a, b, such that f of c equals w. Boy, that is a big statement, isn't it? But what does it mean? Alright, darn, this watermark's annoying. So let's look at this. If f, if a function, well that's the blue thing here, that's our function. If that's continuous, it is continuous. I could draw that without lifting my pencil. On the interval a to b, yep, from a, which is right here, to b, which is right here, this is definitely continuous. So if that's the case, and if w is any number between f of a and f of b, well look, f of a is the output for this a value, right? The output is, or the y value is, right there. And the output for this b, or the y value for that b, is right here. And if w is between them, yes, w is between them, then there must be at least one number, c, within that interval, such that f of c equals w. Yeah, here's c, it's between a and b, and f of c, or the y value for c, is w, which falls between fa and fb. Okay? I'm going to give you some real life examples of this in a second. I think it'll be clear exactly what this is stating. By the way, there could be more than one number. I mean, obviously there's not in this case. You can actually see the graph. But it's possible that with the intermediate value theorem that there's actually more than one number that falls between f of a and f of b, in which case we're calling it w. Okay, there could be more than one. And if it's discontinuous, then it may not possess the intermediate value property. So just let me do a quick sketch here to show you why discontinuous would not guarantee this. So here's my Cartesian plane. Let's say the function goes like this, and then there's a break, and it goes like that. So definitely not continuous, right? So if this here is point A, and this here is point B, so this is f of a right here, and this is f of b right here. Whoops, a little bit off the grid, but you get the idea. What the intermediate value states is I could pick any y value in between here, like right here, w, and there'd be an x value that's associated with that on the function. But in this case, that's not true, right? Because it's a discontinuous function, there is no point on this function that has a y value or an output value of w. If it was continuous though, so I'm just going to fill this in, if it was continuous, then yes, there absolutely is one of them that is right there. That would be your c right there. That's the point that has an output of w. And just to say it again, it's even possible that there's more than one. I'm sorry, it's not the best. That's not supposed to be completely vertical. But now if you look at it, you actually have a whole bunch of points that have an output value or a y value of w. So you'd have like C1 here and C2 here and C3. You'd actually have 3 of them. So intermediate value is just an existence theorem. It guarantees that there's at least one. It does not mean there's not more than one. And also it doesn't tell you where the points are. Okay, so it's not the most useful thing, but We actually use it a lot in calculus, even when it's almost like assumption that just sits there in the background. Anyway, here's some real life examples of this if you're having a hard time picturing what I'm talking about. Think about a child's height. Let's say that at age 13, someone comes into grade 7 or 8 or whatever, and they're 5 feet tall. And then by the time they leave high school at age 18, they're 6 feet tall. Okay, now this is a continuous function. If you're to graph someone's height over time, right, here's time and here's height, there should be no gaps, even if they grow really fast, right? They're growing, they grow fast, they don't grow much, they grow fast, whatever. It's continuous. So what needs to be the case then if they started at 5 feet and they went to 6 feet by age 18? What needs to be true is at some point, I don't know when it is, but at some point they must have been 5'6". And at some point they must have been 5'2". And at some point they must have been, you know, whatever. You could do every single thing between 5 and 6. It's kind of common sense, right? Well, of course, someone can't just skip over heights. But I think when you use the real life example, it helps you understand what we're talking about here. So here's another real life example. Temperature outside. Let's say at 5 o'clock in the morning, it's -13. Oh, I think I meant to put -3. That's -13 degrees Celsius. Wow, that's really cold. And somehow by 1 o'clock, it goes all the way up to 6 degrees. That's quite a change in temperature there. I guess it's possible though, isn't it? So from -13 up to 6 degrees. So there must have been some point then, some point between 5 o'clock and 1 o'clock, where the temperature was 4.562318. And in fact, why don't I also make it more complicated? I'm going to say the 318 repeats. Okay, 4.562318, 318, 318. There must have been some time that it was that temperature. Right? I know it's a very specific temperature, and I have no idea when it was that exact temperature, but there had to have been some point. In order to go from -13 to 6, you got to pass through this one, so it must have been at that point somewhere. That's basically the idea with the intermediate value theorem, right? If it's continuous and you know two outputs, there must have been some intermediate output that occurred somewhere between A and B here. So here's the sort of questions that you'd have. Use the intermediate value theorem to show that the function f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0, 0, 1. So this is often what you're doing with these, is you're using the intermediate value theorem to prove how many zeros there are, and to get maybe approximate estimates of where the 0 is. Remember, a 0 is if you graph a function. Okay, here's some strange function like this. The zeros are literally where it has a y value and output value is 0. Okay. Now you'll notice that what happens when we go from, and if we start here with the function, think of all the y values of these points here up until that point there. Think of all, what do they all have in common? All these points down here, they're all negative. And then what do all these ones have in common up here? They're all positive. Positive, 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 positive y value 0. Then we go back down to negative again. Negative, 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 all negative. And then we go back up to positive again. Oh, and 0, of course, here. So how do you know where the zeros are? It's where the sign changes. It was negative here and it was positive here. Well, if you went from negative to positive and it was continuous, there must be some point where it was equal to 0. I might not know where it is, but I know it must be somewhere. So let's show you how this works. If f of x equals this, and we want to test this interval 0 to 1 inclusive, let's try f of 0 first of all. So we're going to plug 0 into these. We have 0 cubed, which is 0, plus 2 times 0, which is 0, take away 1, so our final answer there is -1. Now let's get f of 1. So 1 cubed is 1. By the way, this graph I drew here, this does not match that, right? Sorry, maybe erase this or something. This graph does not match this function here. So I'm putting 1 in there. 1 cubed is 1. 2 times 1 is 2. Then I subtract 1, and I get 3 minus 1 is 2. Okay, now look, what happened? We went from a negative to a positive. I'm even going to write in here. Sign change. So let me redraw this. If at f0 it was at -1, and at f1, so here's 1, at f1 we were at 2. Guess I could put some tick marks here. So we're at -1 and now we're at 2. This function, I don't know where it happened, but if it was continuous, this function had to have at some point cross the x-axis right there. And that is where your 0 is. So do I know exactly where it is? No. But I know that there must be a 0 between 0 and 1 on the function. Right? There's no way to go from -1 to 2 without crossing that x-axis, unless it's discontinuous. But we're dealing with continuous functions. This is a polynomial function here, and polynomial functions are continuous. So I've done it. I've proven that there must be a 0 between 0 and 1. Next one, is any real number exactly 1 less than its cube? Okay, we're going to write a little equation here. Let's let the number we're talking about, let's call it x. So it's saying, is any real number exactly 1 less than its cube? Well, what's the cube of x? X cubed is what that means. You take x cubed, and the question is asking, can you do 1 less than that and end up back at the actual number, back at x? So this is what we're wondering. Is it possible that x cubed minus 1 equals x? Okay, well, let's set the x, let's set it equal to 0, right? Let's bring this x over. So we have x cubed minus x minus 1 is 0. So basically what we're doing here is very much what we did in the last question. We're looking for 0 for the function f of x equals x cubed minus x minus 1. We want to know, is there some point where the sign changes from negative to positive or positive to negative, because in which case we're going to have a 0 there. Now in this case it's a little bit more difficult because they didn't tell you, in the previous question they told you check out the interval 0, 1. Here they didn't tell you where to look. I mean, heaven forbid, what if it was like, oh yeah, there is one between 99 and 100. I mean, I don't want to plug in tons of numbers. But look, we do have a lot of small numbers here. Why don't we try some stuff like f of 0. I mean, I'm kind of cheating. I know what the answer is. But let's try f of 0, f of 1, f of 2, and hope that that works for 1 ohm. Guess what? It will work. So we plug 0 into here. F of 0. So 0 minus 0 minus 1. 0 minus 0 minus 1 equals negative 1. Okay, now let's put 1 in there. 1 cubed is 1. And then we're going to take away another 1. And we're going to take away another 1. Which equals negative 1. So does that show us there's a 0? Not yet. It's still, this function's still below the x-axis down into the negatives. We need it to go positive. Let's try 2. 2 cubed is 8 minus 2 minus 1. That equals 5. Oh, there you go. There's a sign change right here. So because there's a sign change, we know there's a 0. We also know approximately where it is. There's a 0 between 1 and 2. Now again, there could be a whole bunch of zeros between 1 and 2, but we know there's at least 1, right? We know there's at least 1 0 between 1 and 2. Alright, use the intermediate value theorem to verify that h of x equals x minus 3 squared minus 7 has a root between x equals 5 and x equals 6. It's practically the first question over again. I don't know why I put this one on here. So it's nice, they've given us the x values. So h of 5 we need to find, and h of 6. And we'd like to see a sign change, in which case we know there's a root or a 0. I know they're not exactly the same meaning, but they're pretty darn close. So I'm not going to get into the difference right now. So I put 5 in here. 5 minus 3 is 2, and 2 squared is 4. Then I take away the 7, and I get negative 3. That's a 3. Terrible. Okay, 6. 6 minus 3 is 3, and 3 squared is 9. And then 9 take away 7 is 2. There you go. We got a sign change. We know there's at least 1 root or 1 0 between 5 and 6 on this function. And the last one, use the intermediate value theorem to prove that the equation x cubed minus 2x squared plus 3x minus 3 has 3 solutions, has exactly 3 solutions. Wow. Okay, the first thing to know is, in polynomial equations, well, let's rewrite this first of all. I'm going to set it equal to 0. I'm going to move everything over here, and I'm going to save a step. Remember back here, once we set it to 0, whoa, what happened to my equals here? Why didn't someone say something? Come on, people. Remember once we had this equal to 0, we said that we could also, we're looking for f of x equals this side of the equation. I'm going to do the same sort of thing here. So, saving a step. F of x equals, I want to move everything over here because I want my x cubed to be positive. So x cubed, 2x squared comes over, becomes negative 2x squared. 3x comes over, becomes negative 3x. And negative 3 comes over, becomes plus 3. So we're looking for 3 solutions, which is kind of like 3 roots, which is kind of like 3 zeros. Oh, I hate the difference between those. They're so close. But anyway, we're looking for the same thing. We're looking for some spots where it goes from negative to positive or positive to negative. And specifically this time, we're looking for 3 of them. Wow, exactly 3. Okay, here's the first thing. Because this is a cubic, right, because it's degree 3, remember what that tells you? That tells you that 3 is the maximum there could be. There could be less than 3 real roots, real solutions, but at most there could be 3. So maybe I'll just start by writing there is a maximum of 3 solutions in a cubic function. That's degree 3 if you want to write that down. Okay, so we know there's a maximum of 3. So if we can find 3, we're done. If we find less than 3, well, I guess we're not. There could be less than 3, but they're telling you in the question that there is 3, so we're definitely trying to find 3. Alright, again, they haven't given us anywhere to start, but let's assume they're not giving us numbers like 7 and 12 and negative 18. Let's try numbers like, I don't know, let's go f of 3 down to f of negative 3. I know it's going to take, whoops, this is f of 1. I know it's going to take a while, but maybe we'll get lucky and we'll find them all before we get there. Maybe we'll get unlucky and we'll only have found 1 or 2 and we got to keep going, got to extend our search. Spoiler, that's not going to happen. How do I know? Because I already did the question. So let's try 3 to start. 3 cubed is 27 minus 3 squared is 9 times 2 is 18. 3 times 3 is 9, and then we have a plus 3. 27 minus 18 minus 9 is 0, plus 3 is 3. Okay, let's try 2. 2 cubed is 8. 2 squared is 4 times 2 is 8. 3 times 2 is 6, plus 3. So 8 minus 8 is 0. Take away 6 is negative 6, plus 3 is negative 3. Okay, there's 1. We got a sign change right there. So that is one spot where there must be a solution, is between f of 3 and f of 2, right? Maybe it's 2.5 or 2.6 or 2.1111. It doesn't help us find it. It's an existence theorem. It shows that there must be one. Okay, let's keep going. F of 1, I know it's awful, but that's a 1. So 1 cubed is 1. 1 squared is 1 times negative 2 is negative 2. Negative 3 times 1 is negative 3, plus another 3. 1 take away 2 is negative 1, negative 4, negative 1. Okay, no sign change. The function's still below the x-axis. Let's go with 0. 0, take away 0, take away 0, plus 3. 0, take away 0, take away 0, plus 3 gives us 3. Oh, we're back above the x-axis. The only way that could have happened is if we cross the x-axis somewhere. So this is another sign change. There's another 0, another solution there. Okay, we just need one more sign change and we're done. Let's do negative 1. Careful your negatives. Negative 1 cubed, negative 1. Minus. Negative 1 all squared is positive 1 times the 2 is 2. Or if you want, times negative 2 equals negative 2. Sorry. Negative 3 times negative 1 is plus 3. And then we've got another plus 3. Negative 1 take away 2 is negative 3. Plus 3 is 0. Plus 3 is 3. No sign change. Got to keep going. Negative 2. Negative 2 cubed, all cubed, is negative 8. Negative 2 squared is positive 4. Times negative 2 is negative 8. Negative 3 times negative 2 is positive 6. And another plus 3. I think we found it, didn't we? Negative 8 take away is negative 16. Goes up to negative 10. Goes to negative 7. And we did it. We got another sign change right here. We do not need to try the next one. But what do you know the sign of this would be if you'd put it in here? It would definitely be negative. There can be no more. Believe it or not, if you did f negative 4, negative 5, negative 620, it'll never change signs again. How do I know? Because of this. There's only a maximum of 3 solutions in a cubic function. We already found all 3. There's nowhere else that if you plug f of 5, 7, 9, 12, 18, 3000, you'll never have another sign change as you go from one to the next consecutive one. Alright, that is the intermediate value theorem. A bit of a strange one for you, but hopefully that makes sense. See you later.